Hello, can you all hear me? And you can use chat box to give me some message. Okay, great. Thank you, Stephen. So this is the end of week 14. And we have 10 people online, but we're going to go ahead anyway. Let me see. So we're going to quickly go through what we talked last lecture about analog motion sensors. So you can see what we have here. So regarding 3 purposes of measurement, so remember, we want to use the measurement to do monitoring, control, and training, okay? So we talked about garbage in, garbage out, garbage in, garbage out, okay? Garbage in, garbage out, meaning the sensor accuracy is very important for closed-loop controls, okay? Then we talk about sensitivities, okay? So then using a definition of a sensitivity, and so you see that for the static relationship, the sensitivity is basically doing a partial derivative, okay? So the control system is basically all matters about sensitivity. Therefore, if we assume the control plant G has some uncertainties, and how this uncertainties will affect the in and out closed loop transfer function. So in the open loop setting, we can see that the sensitivity is always 1. It's always 1. So that means garbage in, garbage out. That means your controller will have no effect about the sensitivity. Okay, you cannot control anything in terms of sensitivity. If you have 10% in the G, you also have 10% in the closed loop, in the input to output. So, but in the closed loop setting, the story is different, okay? So we have a handle, I use the word handle. We can tune, or knob, we can tune the sensitivity by increasing the control gain, okay? So, but on the other hand, the sensitivity is not by coincidence, but it's actually an interesting thing to think about sensitivity using superposition principle. P is called a closed loop transfer function. S is that sensitivity, okay? Here, okay? Look at it here, sensitivity. So then we moved to analog motion sensors, talking about displacement, velocity, acceleration. We explained why we cannot simply use an ideal. This is called ideal differentiator, okay? Because of the noise amplification in a very high frequency. If you have very high frequency here, so your magnitude of amplification is also very, very high, okay? So we still need analog motion sensors, analog speed sensors, acceleration sensors, and so on and so forth. Okay. So the rule of thumb is when you choose, it depends on how fast the motion is. For the low frequency applications, like 1 Hertz to 5 Hertz, or less than 10 Hertz, okay. Those displacement measurements usually provide very good accuracy. So, but in like 1000 Hertz, it's better to measure velocity. Okay, velocity. Okay. If you have very high noise level, high frequency motion, then it's better to use acceleration. Then you integrate the acceleration, you'll get speed. The integrated get a position. It sounds very rosy, very rosy. Okay, you have one, you can save money. Unfortunately, by integration, you are going to introduce the low frequency drifting. Okay. Anyway, so we've spent a lot of time talking about this typical specs for analog motion transducers. We have 5 categories of specs that is in common we should care. The first is the frequency range of interest. Frequency range of interest, you should be have a clear idea about what the range. Then output impedance, typical resolution, accuracy, and sensitivity. So, but if for any specific sensor or actuator, the spec sheet can be multiple pages. Sometimes it's like a book. Okay, so there are lots of details about the sensor and the actuator. So when you do the survey, please not only focus on these 5 specs, okay, typical specs. You should also pay attention to the specific parameters for that specific sensor or specific actuator. So we spend some time talking about potentiometer, and everybody believes the potentiometer is just some piece of cake. But I give you a clear warning that it's not like a case. Depending on the what I call loading effect, loading effect. So we use the simple angular motion potentiometer configuration to measure the theta, and it turns out that the percentage of the theta, this is the percentage of the theta, is actually non-linearly related to the output voltage. So by some derivation, you are going to see a arrow in here. So this is supposed to be linear, but it is in reality it's not. So let's see what the non-linearity looks like. It looks like this. So the displacement theta over theta max is like how many percent of your travel of your slider or wiper or arm with respect to the output reading of the voltage over the reference percentage. So this is just like a voltage divider, okay? But they are not proportional. You thought it is not, okay? So this is unfortunate, and a lot of people ignore this. I want to remind you one more time that remember we did a quiz, and now we firmly believe using a simple cascaded 2 voltage dividers using potentiometer, this is not 2.5, okay? It is actually 2.0. I hope this is a lifelong lesson you can remember. So the loading effect is very important, okay? From that, we learned the impedance matching, and also we learned the importance of op-amp, okay? So all these things are very essential knowledge for fundamentals of mechatronics. So the error could be very big, like 70% of the error, okay? If your load is small and RC is big, so that's the case. But remember, let's go back to this one, and we in this table we placed the arm in the middle, okay, in the middle. but usually you have the whole range, okay? The range, whole range, okay? So when you read sensor specs, sometimes they will tell you a term is called FS. So we call the whole thing is called, whole range is called full scale, okay? The full scale. So in here, we discussed about these numbers. You have to talk about what scale. So in here, you have like 0.5 is 0.5 full scale, okay? That means we are talking about the arrow in here in the middle. So this is half 0.5 full scale. Otherwise, you are talking about here, okay? So I told you limitations of displacement measurement device. Usually you have a mechanical contact. So have slow motion about 5 Hertz, okay? 5 Hertz. 5 Hertz is also a bandwidth for a human actuator, your arm, okay? Your leg. The benefits, of course, is less costly, it's cheaper, widely available. You have a high voltage output signal. It's usually high. You don't have to use the amplification, okay, in many of the applications. So again, this will save a lot of cost, okay. But the sensitivity is another problem is that the impedance may change, okay? If you change the coil resistance or supply voltage change, and so on and so forth. So this type of potentiometer actually is still widely used in industry for its robustness and for its low cost. So these are some exercise. I don't want to go through too much. So I'm going to today start from, this is our week 14, lecture B. We are going to talk about other analog motion sensors. And if time allows, we are going to talk about digital transducers. So one of the important classes of transducers is called variable inductance. Inductance is changing, okay? Remember inductor? You have a coil, so you know, capacitor, you have resistor and inductor. So that's inductance, okay? The principle of electromagnetic induction, using that, then you have variable inductance transducer. So basically you have a flux linkage, you have electric conductor. If those linkage changes, the flux changes, okay, flux changes. So then you will have voltage will produce in a conductor. Okay, who said that? Who said that? This is Maxwell's principle, right? So they will generate a magnetic field can oppose to the primary field. So magnetic force is necessary to sustain that kind of flux linkage. So if the change in the flux linkage is brought about by a relative motion, so usually you have a relative motion, that's a displacement. So this kind of motion, mechanical energy, will be converted to electrical energy. So these are just the high school physics, electromagnetics. So this is the fundamental idea behind this variable inductance transducers. It's called electromagnetic induction. Okay. So usually we talk about how to translate the motion into a flux linkage change, and that flux linkage change will produce induce voltage, okay, change in the inductance used as a measure of the motion. So that kind of conversion. Okay. So different types of variable inductance. There's something called mutual inductance. There's a self-induction and permanent magnet. So this is probably the easiest to understand. But let's take a look about this one by one, okay? So there's another idea is talking about changing the ferromagnetic medium, the medium, okay? We'll see some ideas about, this is also a variable reluctance, variable reluctance transducer. So those mutual inductance transducer, most of the self-inductance transducers, all of this type, involving the change of this media, okay? So if somebody tells you a permanent magnet, the PM transducer, the PM transducer is variable reluctance, just tell them this is not correct. So PM transducer is not variable reluctance at all, okay? So we're going to first focusing on a mutual inductance transducer and talking about differential transformer, okay? So I think it's good to see the picture before we go through the text. I probably will not come back to this, so I'll explain to you while in front of this picture. So this is called LVDT, linear variable differential transformer. So usually use this one to do a displacement measuring device. So then compared to potentiometer, they have obvious advantages, okay? We're going to talk about it. And the LVDT itself is changing the reluctance, okay? Changing the reluctance. And the passive transducer, the measured displacement provide energy for changing the induced voltage. So let's talk about this through the picture here. All right, so this is a cup in the middle. So then, so this is called insulation form, okay? So these are insulation form, okay? Insulation form. So when these are coils here, so this is the primary coil. You put external voltage in here, and inside the coil, they are produce magnetic field, okay? Magnetic field, okay? Magnetic field. Inside the magnetic field, they will cover, okay? They will cover, this is a magnetic field. So this is called primary winding, okay? Primary coil. So when you have an external voltage applied, they are going to produce a magnetic field, okay? Now, you have a ferromagnetic core in here. So this is ferromagnetic. So they have a magnetic reluctance, okay? So then you have a coil in here, okay? In here. And if you have a relative motion of this bar, okay, the core displacement, this core will move left and right. While you move, you are going to induce, okay, you are going to induce, okay? You are going to induce the current in the coil, okay, in the coil. And you connect this left secondary coil with the right secondary coil. So by doing that, you can imagine, if I stay in the middle here, so there's nothing, it's zero, okay? Okay, stay in the middle, okay? If I go from left, then I'm going to have something like this. If I go right, I have something like this. These are the voltage level we'll be seeing from here. Okay, VO. Okay, VO. Um, but if you get out too far away, then I don't have anything because I'm out of the electromagnetic field. So here is all zero. So nothing. But if you have it quite in the middle, half in the air, half inside, like here, half in the air, this is air, half inside. So then you probably will have a serious non-linearity in here. So that's kind of saturation and going down until you get zero. So this is what we want. It's called a linear range. Okay, linear range. So you only have a valid range until here. Okay. So I hope this makes sense to all of you about LVDT. LVDT. So I have a question for you. So what if you have 2 times of Vref? I double the voltage in here, what I'm going to get. Okay, so I'm going to have a doubled voltage in here as well. Okay, okay. So but the same, but the linearity range is the same. Okay, the same. But if the Vref is too big, you know, if this is too big, okay, the magnetic field strength will saturate. Okay, so you remember there's a magnetization curve, something like this. So this is your current. So you increase the current. So this is the magnetic field B. So it's something like this, right? So you will saturate. But remember, if you reduce the current, you'll get something here. So do you know this type of thing? You have seen this one? This is called magnetization hysteresis curve. Okay, hysteresis curve. Okay. So, but in reality, okay, in reality, this is probably not using DC current. Okay, they're probably using AC current. Okay, okay. Then it's a very different working principle. Then your output is kind of modulated. Okay. So this is the simplest form. You have cylindric insulating non-magnetic form has a primary coil. So I have said this already. Let's go quicker. So in a easy way, you can see this is a primary coil. You produce a magnetic field. You produce magnetic field. This is also sometimes called field excitation. Field excitation circuit. So you produce the field, okay? Magnetic field, okay? So then if you have a core move left and right, so you are going to produce a voltage in here. While the connection is, you can see, I go from here. If I have a current going from here, the current will flow in this way and come back, it flow this way. So this is some sort of differential form. So therefore, this is called differential connection. Differential connection. Okay, so then there must be a neutral point. This is a zero. Okay, neutral point. And stay in the middle, everything will be zero. It's balanced. So it's called null position. Okay, null position. So if you want to use LVDT, measure the displacement, and it can measure the transient motion very accurately. Okay. Sometimes you use the reference VREF, you make the reference voltage called a carrier frequency. It will be 10 times larger than the largest significant frequency in the measured motion. So in other words, if you buy a LVDT, so there must be a parameter it's called carrier frequency. So the higher frequency, the more expensive. Okay, more expensive. Okay. So the performance of the LVDT is sensitive, and also sensitivity and accuracy will improve if you have that excitation frequency higher. Okay. So advantages, you should know that. Let's go through that. So first of all, the motion and the device is non-contact. Okay. Okay. All right. And so the hysteresis is negligible. I told you hysteresis. So this hysteresis goes magnetic hysteresis about this magnetic magnetization curve. And sometimes you have a mechanical backlash, especially when you have a gearbox, then you have this backlash. And output impedance is low, so it's around 100 ohm. Okay, so signal amplification is usually not needed. Okay, not needed. That's good. Okay, you don't need an amplifier. And you can do positive, negative. You have a directionality. Okay, direction you can get from the positive or negative of the voltage. Can be very compact and small, like 1 cm. Okay, and if you use this is very interesting. Can you take a look? So for 1 cm long, 1 cm size, and your travel is only 2 mm. Okay, so centimeter with a millimeter is 10 times. So in other words, your physical size of LVDT is like, oh, I have a size of 50 centimeter long, like half meter. Okay, half meter, like 1.5 feet here. So what's the travel you can really do? Maybe 2 centimeter here. 2 centimeters. It's quite small, quite small. Okay, so it's like 2%. Okay, so this is one. It's a 20%. I'm sorry, 20%. 20%. Then this is if you have 100 centimeter, that 100 centimeter is 1 meter, right? 100 centimeter, then you have a 20 millimeter. Okay, so then 50 centimeter, you have a 10 centimeter. So this is 20%. Okay, this is only 20%. So this is 20%. This is a 10 mm. You have 10 mm, you have 20% of this valid travel range. Very inexpensive, durable, and robust and simple. It's very fine resolution. Okay, so in theory, it's infinite. Okay, like so high. So this is really used in practice a lot. It's way much better than a coil potentiometer. Okay, the coil potentiometer, so you have a wire, you have wire width, so you have wire. The distance that will limit your. So maybe the maximum is 0.1 mm. That's already a very fine, very tiny, small diameter of the wire. So that's for LVDT. So you got an idea, LVDT. You got an idea, okay? LVDT. But you can imagine we can have RVDT, okay? Rotational, okay? Rotational. It's a similar idea, okay? Let me show you. It is still a variable reluctance, okay? And so again, you have to bear in this in mind that you always have a linearity range, okay? Linearity range. So here is the idea. I still have the same primary and secondary winding coils. So primary coils to produce the magnetic field, okay? So then you have this is called a pivot point, okay? Pivot point. Then you have left and right rotation. While you rotate, say for example, you rotate in here. Okay. So then you rotate. So this is the angle you rotate. Okay. When you rotate, you can see that the magnetic field, okay, the media inside the media of this magnetic circuit will experience different reluctance. So reluctance, okay. Reluctance. It's like a resistance, but it's in a magnetic circuit. Okay, magnetic circuit. So this is called reluctance. So reluctance will change while you rotate. Okay, while you rotate. Excuse me. So then, because of that change in the reluctance, then we are going to induce the voltage inside the left and the right secondary coils. Then during this differential connection, you have output V. So the V versus your theta will have something similar like this, okay? Like this. But we should really focus only on this linear range, okay? Linear range. Okay. Yes. So this type of variable inductance devices induce the voltage generated through the rate of change of the magnetic flux linkage. So the displacement readings distorted by velocity, okay? Similarly, velocity readings are affected by the acceleration. So this is reasonable. So if you do not move smoothly, so the signal will get distortion, okay? So far we did three categories. Let's go back and review it. So first is mutual inductance. We just talk about LVDT, RVDT, okay? So we're going to have example of self-inductance. Then we talk about permanent magnet, okay? So this is a mutual induction proximate sensor. Let's look at the picture first. Say, for example, you have an object, okay? You have object, and this is like a head. You can attach this head into a piece of motion body. So then you put that on. Then when you close this ferromagnetic target object, say for example you have a wall, okay, the wall with like metallic wall, okay. So when you go from here to here, the reluctance is getting smaller. So then So because you have a magnetic field, okay. So when you have a motion up and down, okay, so then the air gap is something like air gap is changing. You can imagine that because of the distance x is changing. So okay, when x is far away, so the induced voltage inside here is smaller. While when you are very close, so very close, you have a very large, okay, very large voltage to come out because of this magnetic reluctance in the magnetic circuit is small, okay. Okay, so this is actually to use this one for what purpose? It's called a proximity sensor. Sometimes you heard about a thing called limit switch. So when you move something, you have something moving parts, okay? You move. Then if you are closer to something, then you stop. You don't hit to that, right? So I want you to stop before you hit it. How you can do that? You need a proximity sensor. So this something is called limit switch. Because usually mechanically they can put a switch in here. If you touch it, you'll make this switch from on to open. Okay, it's something like this. So it's a on. Once I have a button in here. So once you hit my button, then this is going to be off. Once you get off, then you can turn off all the power supply in here. Okay, so that's called a limit switch. But limit switch is kind of mechanical. You have to touch it and turn it off. Okay. So this is no good. Sometimes this when you use it so often, then you'll be in big trouble. Okay. So you hit it, you can damage it, or sometimes you have a huge acceleration, you may hit it and damage it. Or you have so many mechanical contacts, then eventually you got to worn out. So it's no longer reliable. I think in your car you have some limit switch. Okay, see whether your door is closed or not. There's an indicator, so there's some limit switch somewhere. Okay, but there are some high-end cars. You don't have to use mechanical limit switch. So this is a mechanical limit switch. Mechanical limit switch, like I showed you here. So they simply use what they call the proximate sensor. Okay, proximate sensor. The fundamental mechanism, the working principle is the same as in this slide. Okay, and the basic idea behind it is called mutual induction. Okay, mutual induction. Again, it's a variable in the variable reluctance. So that is called proximate sensor. There's also something called a resolver. Resolver is not used so often. In the old machines, they're still using that. So you can think about this is kind of analog type of device to measure the motion. So this is called mutual induction displacement transducer. You need a relative motion between a primary coil and the secondary coil. So you have change in flux linkage. So it's not a variable reluctance transducer because we don't use a ferromagnetic moving elements. So that's a resolver. So widely used in measuring angular displacement, angular displacement, theta. So let's take a look how it works. So again, I said there is a single two-pole winding element energized by an alternating current supply. So this is AC, it's AC supply, okay? And rotor is attached to the object. The rotation is being measured, okay? The stator and rotor. So you have stator, so you have two sets of windings. So you have 90 degrees apart. Don't worry about this. Let me show you this one. So, okay, so basically you have stator, you have a rotor, okay? The rotor, okay, is something I want to measure the theta. This is changing, okay? But I have stator to provide, stator is to provide magnetic field, okay? So then when you have a rotation, okay, rotation, then you are going to have the output induced on this. So this is proportion to sine alpha. Yeah, basically you have this sine cosine, and then I use some processing. We can turn this to find out what is my theta. Or you use that small range. You remember, this is my sine. This is also my sine. I only use this side, okay? There are some thing called self-induction transducers. Let me see if I have another thing here. Yeah, this is self-inductance proximate sensor. So in this case, I have ferromagnetic in here. So inductance measurement circuit, you have AC power supply. Okay, this is power supply. So then it's possible you can measure the whole thing. Again, you can attach this one in it's called head. You can attach this head, then you measure it's similar to the proximate sensor, okay? The third category last category is called permanent magnet transducer. This is actually permanent magnet. So in this case, I don't have a winding, okay? I don't have another winding. So these are the coils. Okay, on top of this this rod. So if the rod moves, moves, then I'm going to produce output signal. Okay, so that is depending on how fast you move. If you stay stationary, then this is not going to be this is a zero. Okay, this is zero. If you move fast, you have a bigger induced voltage. So this is called rectilinear velocity transducer, and this is more commonly used. Simply say I have a permanent magnet to provide a magnetic field. So then I have a commutator, put it here. So you have a rotation coil. So depending on how fast you move, okay, then the induced voltage produced will be different. So most of the permanent magnet tachometer generator principle is using the fundamental block diagram like this. Okay, so all these rectilinear versus for rotational. So in other words, your V0 will be proportional to your omega C. Okay, omega C. And here, your output voltage is proportional to your velocity V. Okay. Another idea is called eddy current transducer. This is used mostly in proximate sensors. So you can use in a dimensional gauging device. or displacement sensors. So it's different, although same idea used in the proximity sensor. It's more like a variable inductance. Okay. So the problem is we don't have to use a ferromagnetic material in here. Okay. We only need a conducting current. A target object is needed. So sometimes a thin film is you put a thin film ferromagnetic thin film metallic conducting material is good enough. So let's see on a figure here. So this is called AD current proximity sensor. So again, you can design it like a head, okay, like a head. Put the attached to the most moving parts, okay, moving parts. So say for example, you have a target object here. You put a conducting surface, metallic. So in here you have a active coil. You have a coaxial table. So then you have a high frequency radio frequency converter. So your power supply is a DC. You convert to a sinusoid 100. Can you see that? Megahertz. Okay, very high frequency. Then you get a signal out for impedance bridge, demodulator, low pass filter, and do calibration. You can output V. So that is the AD current principle, because once you move near this one, the main principle is due to the AD current effect. Okay, so you use the bridge. You have seen this before. So basically, the analog sensors, there are still many such sensors around. I hope some of you will focus on some of those analog motion sensors. I think you have a pretty good coverage about analog sensors. So now it's time we go through some of the digital motion sensors, okay? Digital motion sensors. So this is important to learn because a lot of people had experience using a shaft encoder. You put an encoder on the shaft of a motor, okay, shaft encoder. So it is actually usually digital, and we want to understand what is this, okay? So advantage for using such kind of shaft encoder, which is digital, over the analog counterparts is resolution can be very high, okay? And when we talk about order size, it's like 4 bits, 8 bits, 16, 32, 64. So usually can be like doing like 12, okay? So 2 to the power of 12 is what? Okay, you have 12 bits. You have 4096. So you can divide 360 degrees by 4,000 intervals. So that's very accurate. Okay. So in shaft encoder, we have 2 types. One is called incremental encoder. Another one is called absolute encoder. So we need to learn both today. Let's do a simple one, okay? So you have a one track, one pickoff sensor shown. So this is the light source inside. You can use an LED light source. You have light. So the light beam will get this one is called a photo cell or photo transistor or photodiode. So that when you have a light, you will generate an output. Okay. then output. So basically, you can pick up a light. When you have light, you have a signal high. You don't have light, it's 0. You have light again. Okay, so that's my V out. Okay, output in there. And these are called slits. Okay, those are small window. It's transparent to let the light green through. Okay, green through. So this is called one track. This is a one track. Okay. So imagine you can do multiple track. Imagine you can do the multiple windows. And imagine you, and all other parts are opaque. It's not transparent. Okay. So the overall, we call this is a code disk. Okay, code disk. There's some code in there. So now I uniformly distribute those windows. Imagine this window is like that's a 10 to the power of 10. So you have this amount. Sometimes you have 500 windows in there. So then you can imagine it's very accurate. It's very precise. Okay. So let's take a look at the disk. Okay. But it's possible that you have multi tracks. Okay. You have, these are 1, 2, 3, 4. You have 4 tracks. Okay. 4 tracks. So this is LSB. So it's here, LSB. LSB means least significant bit. So you have a 1, 1, 1, 1, but this guy is LSB. So the highest one is called most significant bit, SMSB. So you have multi tracks, but these tracks can extend. Okay, these tracks can extend. Imagine these are 4 tracks. Okay, but what if you have 10 tracks? Okay, so this disk is kind of called code disk. It's exactly interesting code disk. In fact, there are 2 types of code. One is called a binary code. One is called a gray code. So this is a binary code. Okay, binary code. So you can see this is if this white is 1, black is 0. So you have 0, 0, 0, 0, 1, 1, 1, 1, now 0, 1, 1, 1, and 1, 0, 1, 1, and so on and so forth. So this is just incrementally. Okay, it's called binary code. Okay, binary code. But this one is interesting. It's called gray code. They can be converted. Okay, it can be converted. But this one you will see that it's interesting. So this is 1, 1, 1, 1. So you can see is a 1, 1, 1, 0. But this one is not the same. It's 1, 1, 0, 0. 1, 1, 0, 1. What do you see the difference? Just from this one, this is sector to this sector, there's only 1 bit is flipping. From here to here is only 1. This bit is flipping. Okay, this bit is flipping. Okay, and from here to here, you only have this bit. This bit is changing, and this bit is changing, and from this one to this one, you only have 1 bit is changing. So every time you go, you only have 1 bit. Okay, 1 bit changing. Okay, 1 bit changing. So this kind of ambiguity in a bit switching can be avoided. So from probability point of view, the error, it can be reduced a lot. So people love this gray code actually from reliability point of view. Okay. So if you use multiple tracks, this type of coded disk is called absolute encoder. It's an absolute encoder. Uh, so the absolute encoder, they can memorize because where you are, absolutely you know how much you turn, okay, how much you turn. While incremental encoder, you only know what changed from last time. So I hope this is clear uh, because every pattern is different. Okay, in here you can see you have 4 bits, so then you have 16, um, 16 of such kind of tracks. Okay, you have 16 tracks, the 4 bits. Okay, 4 bits. So then you can divide this angle 360 divided by 2 to the power of 4. So this is not a high resolution. If you need more, you need more tracks. You need to add more tracks. Okay, more tracks. Okay, and different patterns. So you can imagine absolute encoder need a lot of such kind of thing. It's way more expensive. Okay, way more expensive. Okay, so in reality, we usually use simple, um, the simple incremental encoder like this. Okay. So interestingly, a lot of people didn't realize that sometimes you don't have to have a slit. Okay. So here I told you need a slit. Okay, the window and it's light. Just let you know, open your mind that sometimes you can use a sliding contact brush contacting here. So you have code disk, you have some dots in here, and so then everything here is electrically insulating material, but this is a ferromagnetic conducting metal area. So, every time you contact this one, then you have a wire going here. So then you can detect there's a pulse in here. Okay, pulse in here. If you contact, then it's going. So this is in contact. This is not in contact. In contact about these dots. Okay. So that kind of using magnetic dots, conducting dots methods, you can see in some of the applications. But I never used this thing before. It's kind of interesting. Okay. So you don't have to use light. Okay. No light. Here we didn't use light. So of course you can use some other ferromatic, non-ferromatic using that magnetic dot, and you pick up all these, and you have a very high frequency primary supply, and you produce all these type of modulated. So this is kind of like a modulated waveform, and then you can use this one to after another circuit, you will be able to recover something like this wave. Okay. So this is using a proximity sensor. You can also do the same. This is called proximity probe encoder. So, but we focus on optical encoder. A lot of time we delete this term because by default everything should be optical. Just a moment ago I showed you several other ways. You don't have to use light. Okay. So let's go to here. Okay, here. Here is an optical encoder, okay, and it's incremental, okay. You only have the window of one track of window like this. You have only one track. Remember, if you have absolute encoder, you have multiple tracks you need, okay, multiple tracks. All right. So let's take a look. So you put a window in here. So this is called a reference window. You can also put a reference pulse pickup point. This is a code disk. You have a pickup point 1 and 2. 1 and 2. I'll explain this one to you soon. Say you have a width of this one, and you put one pickup here, one pickup here. Okay. So what do you see? Just these pulses. Okay, these are pulses. One is from pickup of V1. This is the V2. Okay, you have V1 and V2. So what you get is just these pulses. While V1 and V2 position-wise, they have 90 degrees phase shift. Okay, you have a phase shift, so 90 degrees phase shift. So by showing the phase relationship, we will be able to see. It is a counter clockwise. It's a clockwise or counterclockwise. Okay. So in A, so A, B, C. So this is B, this is A. So in A, this is A, okay, and this is B. Yeah. Depending the direction you move, okay, you will be able to see which is turning clockwise or turning anti-clockwise by comparing V1 and V2's phase relationship. We can know, okay, we can know. And this is for every revolution, every circle, then I will have one pulse coming out, then another pulse coming out. So this is here, okay, this one here. So that's the beauty of having a two pickup point, okay, two pickup point, okay, and having a arrangement. This is also called quadrature arrangement, okay, quadrature element. In many of the modern designs, they use this quadrature element, okay. And all these three pulse counting. So then you need a hardware to count the pulses, and you can do pulse counting or pulse timing. So you microprocessor, you have timer, you have counter, okay? You have timer, okay? But so this one you can use to do that. But good news is that there's already dedicated encoder chip. You just put in the encoder signal in here, they will give you numbers, okay? So within this chip, you need counters and timers. So for microprocessor, you have those resources already, counters and timers. But how to use op-amp, how to use op-amps to count, how to use op-amp to count and time. So all these things in the dedicated course is called ENGR 1656. It's called electronics, especially digital electronics. Okay, digital electronics. I don't think you need to design this type of chip. You just understand how the electronics, how they work. So our timing is good. So here's I'm trying to explain to you the quadrature signal addition. So you can use the V1 plus V2 to form a signal like that. Then you'll have different levels. Okay, 1, 2, 3. You have different levels. Okay, like this. So this one actually will make our physical resolution to improve by 4. Okay, improve by 4. So let's focus on this one, okay? So this is, if we buy a real encoder, it looks like this, okay? So you have 1, 2, 3, 4, you have 5 terminals here. So one of them going to ground, one of them going to power supply, VCC, okay? And channel I is called channel index, okay? Channel index. And A is in the middle, okay? A is in the middle, B is on the side. So these are kind of convention. It's usually used in the spec sheet they will give you. And also these are spec sheet numbers. So let me introduce you. So these are just the logic signals, like pulses, 0 and 1, you know, those are logic signals. Then when you connect to the next stage, you probably need to add a circuit like this. So you pull out this one, connect to the power supply, and the 2.7K is suggested. The reason we do that is if needed, we can enhance the current, okay, of this logic to maintain its voltage level. So the whole thing here has a name. It's called pull-up circuit. So this is in the digital control, especially in the TTL logic, transistor logic. It's widely used. Okay, so if you don't have this one, is it okay? Maybe still okay. Okay, but with this one, we'll make it all your circuits more reliable, not so much influenced by the external disturbances. So supply voltage, you have supply current is about 40 milliamp. Okay. Then what is the resolution? Okay, the resolution means you have 500 pulses per revolution. So I want to ask you how many windows? How many windows? It's 500 windows. Okay, 500 windows. But because of the quadrature use, and we use some of this decoding encoder, this is called encoder, digital encoder. So we have a decoder circuit. There's a dedicated chip to do the job, okay? So because of the two channel in here, A and B, in this hardware level, they already can resolve it to give you 4 times of the physical resolution. That's here is 2000 pulses per revolution. That's a lot, okay? That's a lot. So you have 2 channels, therefore you have 4x. And in here, I don't have an index for this specific incremental optical encoder, okay? And then how fast you can move? 30,000 RPM, okay? 30,000 RPM. If you don't have an idea, I'll tell you. RPM stands for revolution per minute, okay? Revolution per minute, so if you buy a disk drive, you know that the disk is rotating, okay, inside. So what is that? Do you have an idea? What is that rotation speed? So for a good server level, I happen to know this one because I was a designer of hard disk drives. I have some patents on this. But for your laptop, so probably don't have this. So I think RPM is expected. Okay. You may wonder why this. So how come it can come out suddenly? So it divided by 60. So they could be divided by 60. So then this is like 90 hertz. Okay. The frequency is 90 hertz. So then times 60. So it's a second, right? So 60 times 90 is okay. So this is 120 hertz. Okay. I mean that's speed. So because of that rotation, all the signals has to be sampled at least 2 times faster than 90 hertz or 120 hertz. So that's our sampling. So your disk drive usually samples at several thousand hertz level. But now we can do how many? We need 30,000, like 1 order of magnitude. Actually, yeah, 1 order of magnitude higher. So this is not possible. You cannot imagine you can handle this one in what? In potentiometer, right? It's not possible. It will damage it immediately. And the shock. So this is a huge shock. This is called shock in terms of G, right? So, it's very robust. So it doesn't matter. So that's why incremental optical encoder is very cheap. And this thing may be at $1 or maximum. That's a $1 level, okay? $1 level is so cheap. That depends on the volume, of course. Our time's up. I think we probably have some other slides, but let me stop here. And now next lecture we'll focus on actuator. We're going to start with DC motors. See, my explanation is the same as what you have learned so far. But again, we focus on the fundamentals. I'll pause and to see if I have questions in the next 2-3 minutes. So let me see how many participate. Only 15 people participated this. That's a poor number. I don't feel happy. Okay. So it's better to stick with the schedule and listen. And if you just say, "Oh, I watch lecture," the question is, it's different. Okay, it's different. I believe. Yeah, so here you have a chance to answer, to ask questions or interact. So, well, yes, our midterm will be graded probably over the weekend. Okay. Anything else you want to ask? Okay. Emmanuel, thank you. Okay. If we don't have further questions, I'm going to stop here. Again, I'm going to upload the video, and so for those who didn't show up, can watch. I know it's very difficult to stay at home for a long time. We have been in this way for a month or not? Yes? Okay. Well, we are part of the history, and like 200 years later, people will mention this period of time in the human history. And we're proud that it didn't stop us to grow professionally, academically. Okay, take care, everyone. Have a good weekend, and see you next Wednesday. Oh, next, excuse me, next Tuesday we are going to have office hour. Okay, office hour. So I will hold my office hour and come and chat with me. Okay. With that, I'm going to stop sharing. I'm going to ready to say goodbye to all of you. Take care. Have a great weekend. Bye-bye. Okay. Bye.